Morning, everybody. Once again, Dr. Salim is here with you guys. As you know, we started a series of SPI question review. So these are all review questions. Try your best to focus on it and understand it. And I'm pretty much sure you will pass your SPI sonographic principle and instrumentation examination from ARDMS registry and a first attempt. Okay, let me share the notes with you guys one more time. The questions, I think we did already 60 questions, and let's do the rest of them. Okay, now you can see here, these are the question. Let's see what the question is asking. The question, if we use a 10 megahertz, a 10 kilohertz transducer with a wavelength of 10 millimeter, what will be the propagation speed of the sound for this transducer, or for the frequency of this transducer? So we have 1 centimeter in a millisecond, we have 100 millimeter in a microsecond, we have a 1 millimeter and a second, and we have 100 millimeter in a microsecond, and then we have 1 millimeter in a microsecond. What do you think? Which one can be the correct answer? Like, what is your opinion? Let me make this a little bit larger, the numbers, so it's more visible, I can say. Let's see this way. I think this much is enough. Okay. So you are absolutely right. The answer is 100 millimeter in a microsecond. Why? Because if you look at here, the frequency, we have a formula for the propagation speed, that a propagation speed is equal to operating frequency times wavelength, or lambda. Now, here we have a frequency and we have a lambda, or wavelength. So this is a 10, and then this is also 10. If you look at here, so another way of this to multiply with each other, and another way of the form of kilohertz is to write it as 1 divided by the millisecond. So this is the only correct answer. Absolutely right. Let's ask this question. Let's look at this question. It is, we scan a CCA for the length of one cycle was measured to be 2 millimeter. It means the wavelength is 2 millimeter, and the time to complete it for one cycle only, it was 10 microseconds. Now, what is the propagation speed for this sound? Simple and easy. One thing is clear, the wavelength is clear, it's a 2 millimeter, but where is the frequency? We don't see the frequency in this question. It is there, but it needs actually two steps to get to the answer. Now we have answers here. It's a 20 centimeter in a microsecond. It's a 20 millimeter in a microsecond. It's a 0.2 centimeter in a microsecond. It's 0.2 millimeter in a microsecond. And then it is 1.54 millimeter in a microsecond. So what do you think? Which one can be the correct answer? I already gave you a hint. You are absolutely right. D is the correct answer. Why? Because look at here. The frequency here is a little bit hidden. So first we have to find, because the propagation speed is equal to operating frequency times the wavelength, or lambda. But we have a lambda or wavelength, but where is the frequency? Now, to know the frequency, we can find out from the timing. It says one cycle to be completed is a 10 microsecond. So it means another formula for the frequency is 1 divided by t. The t here is that time to take one cycle. How much time is 1 over 10? So 1 over 10 is, I believe that will be, we can say 1 over 10 is 0 0.1. So 0 0.1 microsecond, and then you have 2 microsecond. Now that is our operating frequency here. Now 0 0.1 megahertz. Now to time this, 0 0.1 times 2 is 0 0.2 again, and that will be the millimeter in a microsecond. Microsecond came from this microsecond, or you can say megahertz. So that is the correct answer. Let's keep going to the next question. Okay, this question, look at here. We scanned CCA, common carotid artery, and the length of one cycle was measured to be 2 millimeter, and the time to be completed for one cycle is 2 microsecond. Now calculate the propagation speed. It is exactly the same question, just we had it earlier, because if you look at here, you don't have any operating frequency here. Again, this 2 microsecond for that one cycle is, we should figure out the operating frequency from here. And now the operating frequency is 1 over 2. 1 over 2 is equal to 0 0.5. Now 0 0.5 times 2 is 10. Now, because we have 0 0.5, so it's 0 and then 0.5. And if we break that times 2, it will become 10. So you have only one digit that side of the point. So it will be 1 millimeter in a microsecond. You are right. That is the correct answer. Okay, good job. Let's keep going to the next question. Okay, this is an easy question. The question is, choose the correct answer for the relationship between the propagation speed and density of the tissue. Now, if you look at here, okay, first of all, which one do you think is the answer? Is it direct relationship, indirect relationship, has no relationship, or sometimes direct, sometimes indirect? What do you think? You are absolutely right. It has indirect relationship. B is the correct answer. Why? Because we have a formula for the propagation speed, that another formula, it's an extra formula for propagation speed of the sound is equal to stiffness of the tissue divided by the density. So density is below the denominator. So it means it's below. So if that number increase, at the other side of the equal sign will decrease. So if density increase, propagation speed decrease. If density decrease, propagation speed increase. So they have indirect relationship. Good job. Let's keep going to the next question. Okay. So this question is, what is the relationship between the stiffness and propagation speed of the sound? Now, it is exactly the same question just earlier. So what do you think, which one will be the correct answer? Now you have the formula that propagation speed is equal to stiffness divided by density. What do you think? Exactly is the correct answer. Direct relationship, because it's above the denominator, right? Okay, now let's see next question. If we decrease the stiffness of material, what will happen to the propagation speed of the sound? Again, same related question. What do you think? It will increase, it will decrease, no change, has no relationship, none of the above. If we decrease the stiffness of the material, what do you think, what will happen to the propagation speed? Exactly right, because they have a direct, just we said direct relationship. So they will decrease also. B is the correct answer. Good job. Okay, let's see the next question. Now, this question is asking, for which of the following transducers do we need to use harmonic frequencies? So what do you think? Low frequency transducers, high frequency transducers, all types of probes, any probe we can use the harmonic frequency for them. For 12 megahertz probes, only we can use the harmonics and none of the above. What do you think, which one is the correct answer? When we use, for which of these probes it's necessary to use the harmonic frequencies? What do you think? It's a simple question. You're right, it is the correct answer. It is a low frequency. Why? Because the low frequency transducers, they create a longer SPL, special pulse length, which is longer. And the longer the SPL, degraded the image quality will be. So for the low frequencies, we understand it penetrates better, but the image quality is bad. So that's why we use harmonics to make the image quality better. So low frequency transducer. Good job. Now let's go to the next question. Which of the following is the correct shape of harmonic frequencies? Like what shape of the harmonic frequency you can see, you can find, or what shape does the harmonic frequency has? What do you think? Is it sinusoidal shape, non-sinusoidal shape, a linear shape, a regular amplitude, all of the above? What do you think? Which one is the correct answer? You're right, it's a non-sinusoidal shape. It means the compression portion come earlier, it come faster compared to the rarefaction area below the baseline. So the above the baseline reach earlier, that become faster. Good job. Okay, next question. It asks that creation of an image from the sound reflection, which with at least twice of the operating frequency is called. This question is actually a definition question. Like this definition is for which of the following options. This is like when we have an image, at least we need 2 times the reflection of the operating frequency. Whatever you use the operating frequency, at least we need double of that for the reflection. For example, I'm giving you an example. You're using 3 megahertz transducer. So at least you need to have 6 megahertz reflection. So what type of imaging is this? That is the question. What do you think? Is it tissue Doppler imaging? Is it color Doppler imaging? Is it a power Doppler imaging? Is it harmonic imaging? Is it a 4D imaging? What do you think? Which one is the correct answer? You're right. Absolutely. D is the correct answer. Harmonic imaging. That is the definition for harmonics. Okay, next question. The next question is asking that operating frequency as known as which of, like, what are the other name for the operating frequency? Is it fundamental frequency? Is it initial frequency? Is it starting frequency? Is it transmitted frequency? Or is it all of the above? What do you think? Absolutely right. All of the above is the correct answer. Even there is another name also, transducer frequency. So they have 5 names. So that is the correct answer. Absolutely right. Okay, let's do the next question. Okay, now, what do you think about this question? What are the first 3 even harmonic frequencies for 2 megahertz transducers? Okay, is it 4, 6, and 8 megahertz? Is it 6, 4, 8, and 10 megahertz? Is it 4, 8, and 12 megahertz? Is it 4, 6, and 10 megahertz? Is it 6, 8, and 10 megahertz? What do you think? Even. So simple and easy. Like we just earlier said in the definition that at least it has to be double of the operating frequency. So now, because the even numbers start from 2, right? So 2 times 2 is 4. That's 1. And 2 times the other even after 2 is 4. So now we have to look for. So there are a lot of 4s. So let's pick C. So there is 4. Now the next even number is 4. 4 times 2 is 8. So it means this. And now the third even number is 6. So 6 times 2 is 12. It means that is the correct answer. Keep it in mind. That is important. Now, this question can be asked another way also. For example, we had the above question for the even number. Now let's do it for the odd number. Now, what do you think? If the same probe, 2 megahertz you use, what are the 3 odd, like in order, the 3 odd numbered harmonics frequencies? Which one is the correct answer? Just look to the above answer question and answers. Just we did it. And what do you think? Which one is here is the correct answer? Okay. Okay. I think you found it. I think. Now let's do it. Look at here. 2 megahertz. Now here is a small carefully trick, or we can say it's a little small thing that you have to keep in mind. In odd number for harmonics only, this is an exception. We understand odd start from 1. The digits, the number, odd start from 1. But in harmonics, that is exceptional. Odd start from 3, not from 1. Why? Because on 1, if you multiply 1 with 2, that will be 2 megahertz. That's operating frequency. It's not anymore harmonics, right? And just we said in the definition, it has to be double of the operating frequency. So 1 is not odd number, and the digits or in the numbers for harmonics only. Now, so it means the odd start from 3, 5, 7, 9, 11, 13, and it's keep going. So here, it starts from 3. 3 times 2 is 6. We have 2 here. So let's see which one is the correct. And now the next one is 5. So 5 times 2 is 10. It looks like A is the correct answer. And then the next odd number is 7. So 7 times 2 is 14. So this is the correct answer. Keep in mind. Very good, beautiful. Okay, now let me see what is the next question. Now, all of the following are related to continuous wave ultrasound, except all the below answers are related to the continuous wave ultrasonography. Because we know we have 2 types of ultrasound. One is continuous wave and one is pulse wave. So all of them are from continuous. One is from pulse wave. What do you think? Which one is the correct answer? Very sensitive, high quality factor, high imaging modality, uses 2 crystal system. An entire cursor is gate for the velocity measurement. When we do velocity measurement, what do you think? Which one is except? Which one is not correct for continuous? You are right. C is the correct answer. High imaging modality. Because in continuous wave ultrasound, there is no image. There is no picture. image is not creating for this because there is no damping material in this probe. Okay, good one. Now let's do this question. Which of the following probe is a specific example of continuous wave ultrasound? So what do you think? Convex probe, phased array probe, a linear array probe, peeled-off probe, all of the above. What do you think? Which one is? This is a simple question. Absolutely, you're right. Peeled-off probe, because peeled-off probe is like a pencil probe. It's like exactly almost like this pen. You see this? So it's exactly, so it uses two crystal system. They do not create image. It's only we use it for the velocity purposes. Absolutely. Mostly we use this in echocardiography. Okay, good one. Now let's see the next one. Which of the following artifact is seen with a continuous wave Doppler? So continuous wave Doppler, when you do a velocity measurement for something special, for example, you look for the mitral valve insufficiency or something. So what do you think, which one is the most common artifact we see it with continuous wave Doppler? Range ambiguity artifact, aliasing artifact, ring down artifact, comet tail artifact, or enhancement artifact? What do you think? Absolutely, you're right. It is range ambiguity artifact. What it means? It means they will give you like the velocity of slow flow, high flow, medium size flow. These all velocity will be coming in one velocity. That will give you one package of the velocity. And then you will be not able to see which one is the peak systolic, which one is the end diastolic. So it will give you everything in one. So that is range ambiguity artifact. Correct. What is the next question? All of the following are related to pulse wave ultrasound except, like we just had a question earlier for the continuous, now we have it for the pulse wave ultrasound. So what do you think? Everything is related to the pulse wave. There's one thing which is not related to the pulse wave. Okay. Produce image, uses one crystal system, has listening time for the same crystal, accurate and velocity more than 2 meters per second, accurate and velocity less than 2 meters per second. What do you think? Which one is the correct answer? Okay. Yep, this time. Yep, you're correct. It is this one, accurate and velocity more than 2 meters per second. This is not the correct answer. So this is the one which should be selected. All of these, yes, pulse wave, reduce a picture. Yes, pulse wave, use two crystal system, one sending the pulse. We can say, no, sorry, one crystal system, it is creating the pulses and it receives the pulses back. And then it has a listening time for on the same crystal to make a picture on that area. And this is accurate when you do pulse wave Doppler. When the velocity is less than 2 meters per second, it's more accurate because it will not give you aliasing artifact. But if the velocity is more than 2 meters per second, this is a worse idea to use pulse wave Doppler on that case. So on that case, this is the correct answer to be chosen. This is good for the continuous wave ultrasound. Actually, continuous wave Doppler, we can say. Yeah, correct. Let's do the next question. Let me see. What is that question for? 2D images are better example of the following. What do you think? 2D, grayscale imaging. Continuous wave ultrasound, pulse wave ultrasound, none of the above, all of the above. I think that's a very simple question. Yes, of course, the B is the correct answer. When we say image, it means a picture. So picture only produced with the pulse wave ultrasound. That is correct. Let's do the 3 more questions, and that's it. 78. Now, backing or damping materials are used in all of the following transducer, except now. This is also a question related to the continuous wave and pulse wave ultrasound. What do you think? Linear array, phased array, pencil probe, convex phased array transducer. What do you think? Which of these ones will not use damping material? I mean, they don't have damping or backing material. What's your answer? You're right. C is the correct answer. Pencil probe, because pencil probe is a continuous wave specific probe. PDF probe and pencil probe are specifically designed or dedicated for the continuous wave ultrasound. They are not producing picture. Pencil probe, most commonly we use it for ABI, ankle brachial index. So that is the correct answer. Okay. Now, Next question. Which of the following is a good example of pulse wave ultrasound? This question and this question almost explaining same concept, but of course different answers. Okay, 2D or grayscale imaging, color Doppler imaging, pulse wave Doppler imaging, or all of the above. Very simple question, clear question, straightforward. Yes, all of the above. Pulse wave ultrasound is all of these are the result of pulse wave ultrasound. Correct. Let's do the last question, but not the least. Okay, true and false. Would you think more damping materials in a transducer will cause longer pulse duration? Or let me make this question more simple. When you have more damping material or backing material in the transducer, it says it will give you a longer SPL. The pulse length will be longer. Is that true or false? Yes, you're right. That's false. That's not true. B is the correct answer. Why? Because and more damping material will we have? Like if you put extra damping or backing material in a probe, it will make the pulse more squeezed and they will delete some of the cycles from that. It will become to the minimum cycles. So keep in mind that is important. Very good. Try your best to practice all these questions several times because I'm trying to give you some explanation also the reasons why this is the correct answer and why this is the wrong answer. So I hope again, if you did not subscribe the channel, please subscribe it. And also, once again, don't forget to share this channel with other colleagues or all those healthcare providers you think they will sit for these ARDMS registry examinations, because SPI or ultrasound physics is in all of the subspecialties. If you do vascular Doppler, echocardiography, general abdomen, small parts, MSK, TCD, breast, or any of these examination, physics is there. So take care, and I believe you will be good if you pay attention to these questions. You will clear your concept. Thanks a lot. Take care.